Consider 1 mole of a perfect gas in a cylinder of unit cross-section with a piston attached. A spring with spring constant K is attached to the piston and to the bottom of the cylinder. The unstretched length of the spring is L. Initially, the spring is unstretched and the gas is in equilibrium. A certain amount of heat Q is supplied to the gas, causing an increase of volume from V0 to V1. It is given that the volume is changed from V0 to V1 by supplying heat Q. Let us look at part A of the question. What is the initial pressure of the system? Initially the gas is in equilibrium, so the pressure inside the cylinder should be equal to the pressure outside the cylinder, which is the external pressure. And in this case, the external pressure is equal to the atmospheric pressure PA. Therefore, the pressure of gas initially equals to atmospheric pressure PA. Part B. What is the final pressure of the system? It is given that the volume is changed from V0 to V1. So the increase in volume delta V is equal to V1 minus V0, which is equal to area of cross section into the final length of the cylinder L1 minus initial length of the cylinder L0. Area of cross section is 1, so this will be equal to L1 minus L0. L1 minus L0 is a change in length of the spring, so this will be equal to delta L of spring. Now let's draw the free body diagram of the piston in the final state. This is the piston, and we have external pressure acting from outside of the piston, which is atmospheric pressure PA, and from the inside of the cylinder we have pressure of the gas P gas, and also we have spring force which will act in the downward direction, F spring, and the value of spring force will be equal to K times delta L, and we have found out that delta L is nothing but V1 minus V0, so this is going to be K times V1 minus V0. The net force acting on the piston should be equal to 0, so sigma F should be equal to 0. So from this we can write PA into cross sectional area A plus spring force, which is K times V1 minus V0 minus pressure of gas into area of cross section should be equal to 0. So from this we get the final pressure of gas to be PA plus K by A into V1 minus V0, and here the cross sectional area is 1, so this is going to be equal to PA plus K times V1 minus V0. So this is the expression for the final pressure of the gas in the cylinder. Let's look at the part C of the question. Using the first law of thermodynamics, write down a relation between Q, PA, V1, V0 and K. So we need to find the expression for Q in terms of PA, V1, V0 and K. From the first law of thermodynamics, delta Q, which is the heat supplied to the gas, should be equal to change in internal energy delta U plus work done by the gas delta W. The change in internal energy of the gas delta U will be equal to NCV delta T, which is equal to NCV Tf minus T naught. It is given the gas is an ideal gas. So for an ideal gas, the value of specific heat Cv will be equal to R by gamma minus 1. Substituting this, we can write the value of change in internal energy to be Nr by gamma minus 1 into Tf minus T naught, which will be equal to 1 by gamma minus 1 into nRTf minus nRT naught. We can replace nRTf and nRT naught with PFVF and P0V naught. So this is going to be 1 by gamma minus 1 into the final pressure of the gas Pf, and the final volume of the gas is V1 minus the initial pressure of the gas is nothing but the atmospheric pressure Pa, and the initial volume of the gas is V0. So the final pressure of the gas, as we have calculated before, it is Pa plus K delta V. So the expression for change in internal energy comes out to be 1 by gamma minus 1 times Pa plus K into V1 minus V0 times V1 minus Pa into V0. So this is the expression for the change in internal energy. Now let's calculate the expression for the work done by the gas delta W. Delta W for the gas is given by integral the pressure of the gas into dV, and at any point the pressure of the gas will be equal to atmospheric pressure plus K times the change in volume, which will be the volume at that point minus the initial volume V0. Therefore, dW will be equal to Pa plus K times V minus V0 into dV. So this implies the total work done W will be equal to integral from V0 to V1 Pa plus K times V minus V0 into dV, which will be equal to Pa integral V0 to V1 dV plus K times integral V0 to V1 V minus V0 times dV. This is going to be equal to Pa into V1 minus V0 plus K by 2 times V minus V0 squared with the limits V0 to V1. So the final expression delta W is going to be Pa into V1 minus V0 plus K by 2 into V1 minus V0 squared. Therefore, delta Q will be equal to delta U plus delta W, and after substituting we are going to get this as Pa into V1 minus V0 plus K by 2 into V1 minus V0 squared plus this is the work done, and the change in internal energy delta U, which we have calculated before, we have got 1 by gamma minus 1 times Pa plus K into V1 minus V0 times V1 minus P naught V naught. So this is the final expression for the heat given to the system.